morning. I'm pleased to introduce James Fraser, who's going to be talking to us about the main phases of the renormalization movement.
Okay. Good morning, everyone, and thanks for coming to the 9 o'clock slot rather than 9:30, as I thought it might be. Just go to that and make that mistake. So this is based on quite a work in progress project, which I actually haven't been progressing very much recently. But I thought it was, I wasn't going to have a better audience than this to present this kind of stuff. So that's the kind of state this project is in, basically. I'm sort of going to be talking about how to understand this thing, the renormalization group. I guess I don't necessarily need to go on about the motivations for that here, but I'll say something. So the renormalization group is kind of a really central idea that comes out of post-war, second half of the 20th century theoretical physics. It's maybe like one of the really big new ideas really from that period. And it's associated with a lot of major theoretical and empirical successes, which are associated with Nobel Prizes. So the asymptotic freedom of QCD, Nobel Prize for that. The kind of treatment of critical phase transitions was also associated with Nobel Prize, I think. Well, I think that's not exactly, but anyway, yes. It also has a very important role in some big conceptual shifts that happen in post-war physics. Specifically, these kind of ideas about effective field theories and running coupling, which kind of led to this slightly different way of interpreting what quantum field theories are. That is going to be one of the themes for today. It seems, and we're going to have a discussion about that one today. Given its kind of importance, we've seen some recent philosophical engagement with renormalization group methods. So it's kind of being brought into a few kind of general debates in philosophy of science as well, as kind of philosophy of physics work. So Bob Batterman was kind of one of the first people to put some focus on the renormalization group, connecting it with kind of debates about interstochastic relations, emergence and reduction. So there's been literature about that. It's been connected to discussions about explanation by Batterman and others as well. So potential candidate for non-causal explanations or mathematical explanations. And then it's also been brought into discussions of the epistemology of science and the epistemology of QFT as well. Porter and I have both kind of tried to develop some kind of scientific realist view of quantum field theory, drawing on renormalization group ideas, and we should mention David as well there. I mean, really that's coming from some of David's work originally. So there's quite a few different debates where people have been drawing on renormalization group ideas. However, most of this work has kind of focused on drawing implications of renormalization group methods for other issues. I'm going to be sort of trying to focus on analyzing the kind of foundational basis for renormalization group methods themselves in this talk. So that's kind of the background project, I guess. And the problem that I'm thinking about here is that it seems like the term renormalization group is potentially ambiguous. So it can be used to refer to different, formally different mathematical objects, and there's also the possibility of different interpretations of those objects. So my, I guess, part of the idea here is it would be good to clear that up so that we can then get back to this project of drawing what the philosophical implications of renormalization group methods are. If we have a better handle on kind of what the renormalization group is or what the various things called the renormalization group are. So the basic project is to kind of try and distinguish different versions of the renormalization group in terms of, and to kind of establish relationships between them. And I've also kind of been pursuing this in an integrated HTS way, so kind of trying to also look at the historical development of these different versions of the renormalization group. But I'm not really going to be going into history too much today. And yeah, so the kind of in progress part of this project is that I've got this question at the bottom: what are the various renormalization group structures that I'm going to try and distinguish? Are they conceptually unified in some way? And if so, what unifies them? That's kind of a question that I don't really have an answer to fully. So the last part of the talk is going to be kind of an admission of complexitude, I suppose, on this question. So yeah, apologies for not having a very clear conclusion. But yeah, might be something we can discuss in the Q&A. Okay. Yeah, so just to say something quickly about the kind of historical side of this project, sort of set the scene. So there's kind of two key periods in the development of this notion of the renormalization group. There's sort of an earlier period in the 1950s. I'm calling this the early perturbative renormalization group. So that's very tied to the perturbative approach to quantum field theory. There were these papers by Stuckelberger, Huisman, and Gelman and Lowe, and they're sort of connected together by Bogomolov and Shirkov, and they're the people who really introduced this term renormalization group. So that's the kind of original origin story. Then there's this kind of weird gap for a decade, and then the renormalization group kind of comes back into prominence with the work of Kenneth Wilson in the kind of 60s and 70s. So yeah, that's important to keep in mind, because I'm kind of going to be suggesting that those two historical episodes kind of produce slightly different notions of the renormalization group. But as I said, I'm not going to be focusing on the history too much today. Okay, so yeah, the plan for what I'm going to try and do in the talk, you just had the introduction. I'm going to make a case for distinguishing two ways of thinking about the renormalization group, or two formal structures which are really distinct from each other, that are called renormalization groups. One I'm calling scheme ambiguity renormalization groups, and they have to do with the freedom to fix the renormalization scheme within perturbation theory in different ways. And then the Wilsonian renormalization groups, which I'm going to suggest we can think of the core idea as being a coarse-grained transformation. And then I'm going to kind of ask this question of what kind of unifies these different versions of the renormalization group, and talk about a few different strategies for trying to tell a story there about why these things are all called renormalization groups. Okay. So the first class of renormalization groups, these scheme ambiguity renormalization groups. So as I said, these structures, so the different renormalization groups are going to consist of different kinds of transformations. The first group of transformation structures is tied to perturbation theory, and as I said, this is kind of the historical origins of these ideas. Yeah, I mean, this slide maybe isn't necessary for this audience, but yeah, perturbation theory, we're dealing with kind of power series expansions for quantities in quantum field theory. What we're typically doing is using this as an approximation technique for approximating quantities by truncating the power series expansion. We all know that one of the things that happens in perturbative quantum field theory as opposed to perturbation theory in other areas of physics is that we get these ultraviolet divergences, so these affinities that appear in the coefficients of the series, in the higher order coefficients. And this leads to the necessity for perturbative renormalization. So this is kind of the background. This is where the term renormalization comes in originally. So the historically first paper that introduces some kind of ancestor concept of renormalization group. They don't actually use the term renormalization group. They talk about a normalization group. Was this paper by Schuckelberg and Peterman, which Alex and I spent many difficult but enjoyable hours reading together when I first went to Berlin. So this was my kind of entrance into history, basically, history of physics. So I'm not really going to talk too much about. I think Mike might talk a bit about this kind of approach that Schuckelberg and Peterman were trying to develop, which is known as causal perturbation theory. So it's a different way of setting up the perturbative expansion in quantum field theory based on causality conditions. That's not really particularly relevant here. I just put it up on the slides. I did want to mention one idea that does come out of this alternative formulation of perturbation theory, which Schuckelberg and Peterman were trying to develop, which is that they gave a particular analysis for the nature of the ultraviolet divergences and the nature of renormalization that follows from that. And the idea is that ultraviolet divergences arise because you're multiplying together singular distributions, so things that have the kind of similar properties to things like the direct delta functions. They're more singular than ordinary functions. Products of singular distributions don't have a general definition in the way that you do. You have the products of ordinary functions, but you can provide a definition for the singular products appearing in perturbation theory. It's just that they're not uniquely defined, so there's some kind of ambiguity in the definition of the product, and this is kind of what's underlying the need to introduce counter terms in the standard approach to perturbative renormalization. This kind of way of looking at the ultraviolet divergences led them to introduce a transformation group, a group of transformations between different ways of fixing this ambiguity that arises from the multiplication of singular distributions, which is supposed to leave the physics invariant. So you can kind of think of this as different ways of, in kind of the modern terminology of defining your renormalization scheme. So, yes, so a renormalization scheme, you can think of that as a kind of unambiguous prescription for assigning finite values to the coefficients of your perturbation series. And there are different ways of doing that, which is something that becomes quite manifest in this causal perturbation theory approach. But you can kind of, you can simultaneously shift the value of your expansion parameter and the value of these ambiguities in the coefficients such that the S matrix remains invariant. So that's the kind of idea that Schuckelberg and Peterman are kind of introducing in this first paper, that there's kind of a set of transformations between different ways of fixing the ambiguities in perturbative QFT, and those are going to form some kind of group structure. I mean, they don't demonstrate that, and the discussion is not very rigorous, but that's kind of the idea. So the other origin point was this paper by Gelman Lowe, who had no idea about Sugarberg and Peterman's work, which was completely independent. They didn't use the term renormalization group, but in their analysis of the short distance behavior of QED, and I think Alex is going to be talking more about the Gelman Lowe paper, they made use of the fact that of one of these ambiguities in the way that you can fix a renormalization scheme, namely that you can impose different renormalization scales. So you can think of this as a kinematic scale at which you impose some subtraction procedure, essentially. This was standardly being done at 0, basically, at 0 momentum. So the kind of what's called the on-shell, the mass shell renormalization scheme these days. That was kind of the only method that was being used up until around now, 1954. Gelman and Lowe's idea was that the fact that you can actually work with different renormalization scales, that can be used to give you some information about the scaling properties of the theory, or at least the perturbative theory, the perturbative model. So yeah, we have this distinction between a renormalization scale and what I'm calling at least a subtraction convention. People use these terms in different ways. And those two elements basically compose a renormalization scheme in my terminology. Yeah, as I said, Gelman and Lowe introduced, they didn't introduce the beta function, but they had something very similar to the beta function, which can be thought of as describing the dependence of your expansion parameter on this renormalization scale, and that gives you information about how the theory's properties depend on the physical scale, so the scale at which scattering is happening, say, the momentum scale at which you're scattering particles. As I said, Gelman and Lowe didn't use the term renormalization group, but we can think of the Gelman-Lowe renormalization group as a set of transformations between different renormalization scales. And yeah, so then we have this kind of first result, I guess, of the paper, which is that if we are going to distinguish these two things, the Sugarberg-Peterman renormalization group and the Gelman-Lowe renormalization group, the Gelman-Lowe transformations are essentially a subset of the transformations which Sugarberg and Peterman are considered. Because the renormalization scale is really just one component of fixing a renormalization scheme. You also have to fix a subtraction convention. So basically you have to decide how much of in the conventional way of thinking about it, you need to decide how much of the coefficients you subtract at your renormalization scale. The renormalization scale, the transformations between different renormalization scales are a smaller set of transformations than those that Sugarberg and Peterman originally considered, but these are the transformations that seem to tell you something about the scaling properties of the theory. Sugarberg and Peterman's original paper actually doesn't talk about scaling properties of theory at all. It has nothing to do with no mention of that issue. Just to summarize the key point of this section of the paper, so what I'm calling the scheme ambiguity renormalization groups, these were the kind of historically original renormalization group structures, and they're sets of transformations between different ways of fixing ambiguities that occur in the definition of the coefficients of your series expansion. And then, as I said, there was a bit of a quiet period. This original notion of the renormalization group wasn't actually particularly fruitful. It wasn't taken up that much in the literature in following on from the papers of Wuppental and Shirkov, which I mentioned. Then Wilson is the one who kind of really regenerates this notion of the renormalization group and puts it, he's really the one who establishes the central place of renormalization group methods in contemporary physics. One thing that really the main impetus for this project is that there do seem to be some substantial differences between Wilson's version of the renormalization group and its early version. So I want to kind of try and figure out what the relationship is there. One difference with Wilson's approach to the renormalization group is that whereas the earlier approach was really tied to perturbation theory and specific features of perturbed QFT, Wilson's approach is not really intrinsically tied to the perturbative expansion. And it appears to be based on quite a different interpretation of the transformations that are composing the structure that's called the renormalization group. Specifically, it's based on this notion of a coarse-graining transformation, so a transformation which eliminates degrees of freedom from your model. And yeah, so Wilson was kind of drawing on contemporary work by Kadanoff in condensed matter, and one of the interesting features of this period is that you have these analogies between QFT and condensed matter playing a really important role, which wasn't really the case in the earlier period. This is just one example of a coarse-graining transformation that Kadanoff was considering, what's called real space renormalization group transformations these days. So if you're kind of considering a spin system, Kadanoff introduced this idea of starting with an initial set of spin degrees of freedom, then dividing up this lattice into blocks, kind of assigning a block spin variable to these blocks, so reducing the number of degrees of freedom from using a single degree of freedom to represent what's going on inside the whole block, and then introducing a kind of rescaling and shifting of the dynamical parameters in the model so as to maintain the same long length scale physics is the idea. So this is the basic idea of a coarse-graining transformation. Wilson sort of took this into QFT and used a path integral approach to formulate a coarse-graining transformation within momentum space rather than within real space. So the idea here is that you can kind of compute some parts of the path integral, the parts of the path integral associated with the higher energy, small length scale physics. So that's this part, and then integrate out those degrees of freedom, so that's the language, and shift the dynamic parameters in the action of the model so as to maintain the same long length scale physics. So that's kind of the momentum space version of this coarse-graining idea. You can also do this within perturbation theory. So yeah, those two cases I was talking about, weren't tied to perturbation theory, but you can do this kind of this sort of coarse-graining transformation within perturbation theory by introducing an ultraviolet cutoff on the momentum space integrals, and then shifting the cutoff, so moving to a different cutoff and doing this same kind of shifting of the dynamical parameters in order to maintain crucial quantities. Crucially, so this is not the same, this transformation between different ultraviolet cutoffs, that's not the same as different transformations between renormalization scales, which Gellman and Lowe used. Here you're actually supposed to be kind of moving to a new value of the upper limit of integration, essentially, whereas the renormalization scale is an arbitrary parameter that you have to fix when defining renormalization conditions. So they're really quite different things. And yeah, one of the key ideas that comes out of this new version of the renormalization group is that we can view these coarse-graining transformations, these various coarse-graining transformations, as inducing a flow on the space of possible theories. And this also gives us a way of understanding the scaling behavior of quantum field theories and other physical systems, such as condensed matter systems. So this is kind of a much more powerful framework than the original Gell-Mann-Low framework for asking questions about both the ultraviolet, the extreme ultraviolet behavior of QFT models, and also the infrared properties. And obviously that's kind of one of the ingredients that leads to this effective field theory view. We now have the question of we've got this new class of renormalization group structures. What's the relationship between them? I wanted to make the point that because there are different ways of implementing coarse graining, that there are many different coarse graining transformations you can cook up. Those will lead to different renormalization group flows in principle. Some of them may not be invertible as well, so it's kind of an often made point that the Wilsonian renormalization group is not really a group. That's kind of a slightly complicated issue actually, because it really depends on what kind of coarse graining transformation you're talking about. But definitely some of the ones that are used in physics literature are not going to form anything like a group. We should probably really recognize the existence of multiple Wilsonian renormalization groups, just due to the fact that there are multiple inequivalent coarse graining transformations. But we can hope at least that the flows induced by different coarse graining transformations are going to approximate each other, at least in certain circumstances and certain regimes. So, for instance, the Wilsonian perturbative renormalization group, those transformations between different cutoffs within perturbation theory, that flow hopefully would approximate the flow of a non-perturbative coarse graining transformation, at least when the parameters are relatively small, when the coupling parameter is small. Maybe we can talk about a cluster of related structures here, related by approximative relations. But so the key point from this part of the talk, so I'm just coming to the end of the second section, is that I want to distinguish, at least initially, these Wilsonian renormalization groups from the earlier Stuckelberg, Peterman, and Gell-Mann-Low renormalization groups. The key point is that the Wilsonian renormalization groups are usually understood as being sets of coarse graining transformations, which are eliminated with freedom, which was not the case in the older approach. Okay, so now on to the more work in progress, and I guess more philosophical part of the talk. So the question of what, if anything, really unifies these different versions of the renormalization group. I think we should take seriously the possibility that there is just disunity here. It's quite, from a historical point of view, Wilson was the one who connects these two periods and continued to use the term renormalization group from the from the Bogolov and Cherkov discussion, basically. That was why he got that term. It's possible that he's just using the same term to refer to something completely different. That doesn't seem to be inconceivable just from a historical point of view. And it does seem like these two approaches do have some important differences between them. The first approach, as I said, was tied to perturbation theory, and the transformations between different renormalization schemes are usually at least interpreted as relating physically equivalent models. There is some, there's not really any philosophical literature about this. There is kind of a debate in physics that emerges in the context of perturbative QCD about how to understand renormalization schemes, because it becomes a much bigger issue in QCD than it ever was in this. The existence of different renormalization schemes wasn't really a practical issue in the earlier period. the problem, I probably shouldn't go on about this, but basically, although the entire series is supposed to be invariant under changes in renormalization scheme, truncations of the series aren't actually renormalization scheme invariant. So there's actually a practical problem about how to fix the renormalization scheme in QCD. And some of this stuff I think is quite philosophically, or it has interpretive aspects to it. And there's at least some views that are taken in the literature which might disagree with the idea that transformations between renormalization schemes relate to equivalent models. I just think those views are wrong, basically. And definitely the mainstream view is that different renormalization schemes just express the same physics. Whereas the Wilsonian approach, as I said, it's not tied to perturbation theory, so we have this kind of generalization of renormalization concepts outside of perturbation theory during that period, which I think is very interesting and important. But also the transformations are at least, well, there's kind of a question here as well about how to interpret what kind of Wilsonian renormalization group transformations are. But there's at least a strand of literature where you will find people speaking as if coarse gradient transformations do not relate equivalent models. So you'll kind of, well, that language though is just talking about eliminating degrees of freedom. You might think, if you remove degrees of freedom from the model, you're moving to a different model. So that kind of language is often used, which is suggesting an interpretation point to which you're really, the Wilsonian renormalization group transformation is really relating different physically equivalent theories or models. And so that's one, that's kind of some background for why you might worry about whether these are really related things at all. You also find quite a bit of interpretive disagreement amongst the historical actors themselves about what the renormalization group is, what's kind of the primary, what's the core notion of the renormalization group, what's incidental. So for instance, these were just two contrasting quotes that I found, but there's more of these. So Weinberg, in this kind of review paper that he writes about the Gell-Mann-Loeb discussion, he sort of has a go at Bogomolov and Shirkov, saying, well, I'll just read it. Bogomolov and Shirkov seized on the point about the invariance with respect to where you renormalize a charge, and they introduced the term renormalization group to express its invariance. But what they were emphasizing, it seems to me, was the least important thing in the whole business. And Weinberg goes on to say that the kind of the scaling picture and the idea of an effective expansion parameter that kind of Gell-Mann and Loeb arguably introduced, although I think Weinberg's definitely reading kind of contemporary interpretations back into the Gell-Mann and Loeb discussion. He basically says, that's the really important idea. This term, he even really suggests that the term renormalization group is a bit of a kind of fancy name that the group nature of the transformations is not particularly significant. Then we have Shirkov. Obviously, Shirkov's biased here because he's one of the authors who introduced this term renormalization group. In a kind of similar review, like a historical review article saying, however, Gell-Mann-Loeb paid no attention to the group character of the analysis, and the RG is nothing else than the invariance of the solutions with respect to its way of parameterization. So here, I think we have kind of two ways of thinking about what's really fundamental to this notion of the renormalization group. One puts the kind of non-trivial scaling aspect first, so the fact that the renormalization group gives you this description of the scaling properties of QFTs, that's really the core idea. And then you have an alternative view which puts this sort of invariance idea first. So really viewing this as like analogous to some kind of symmetry, or the existence of ambiguities in your theory and the ability to transform between them is the key idea behind the renormalization group. Okay, so I'm going to talk about kind of a few thoughts about how you might respond to this worry about disunity, and kind of make the case that, you know, there is good reasons for calling these things, all these things, renormalization groups, despite the differences between them. So they're kind of going to go in 3 strategies in order of ascending strength, I guess. So the kind of weakest point I wanted to make is there definitely are lots of formal relationships between these different renormalization group structures. The first one I talked about was, you know, the Gell-Mann-Low renormalization group is really a substructure of the larger Stuckelberg-Peterman renormalization group. That's fairly straightforward. There's also kind of mathematical physics work that's been done on kind of trying to pin down rigorous connections between the Wilsonian renormalization group and the Stuckelberg-Peterman renormalization group. This is within perturbation theory, though. So this paper by Dutch is basically trying to, the idea is that elements of the Stuckelberg-Peterman renormalization group can be used to systematically approximate the coarse grained transformations you get from changing the the kind of UV cutoff within perturbation theory, which goes some way to kind of explaining why they both the Gell-Mann-Low renormalization group and the Wilsonian renormalization group both kind of tell us something about the scaling properties of the theory, at least within perturbation theory. And then we had this idea that I was saying before that, you know, although there may be different Wilsonian renormalization groups corresponding to different coarse grainings, you know, hopefully there's going to be kind of approximative relationships between those different structures. I think I meant the perturbative Wilsonian renormalization. So I have a picture which hopefully will make this a bit clearer. So this was my kind of diagram of my current understanding of the kind of work that's been done on relationships between these structures. So yeah, as I was saying, there's been some kind of rigorous work trying to kind of argue that there's approximative relationships between the perturbative Wilsonian renormalization group and this kind of older Gell-Mann-Low approach. And then, yeah, hopefully these transformations are going to approximate non-perturbative coarse graining transformations, and then there's going to be approximative relationships between those. So yeah, one way of kind of trying to unify them is to say these are a constellation of structures which have various approximative relationships between them, and that explains how they can all tell us about scaling properties. This is kind of a fairly weak view, though, because you wouldn't necessarily be saying that anything kind of, it's purely formal relations, basically, rather than any physical interpretation that's core to all of the different structures necessarily. So another strategy would be to try and develop a kind of common interpretation of these different renormalization group transformations. And yeah, as I was saying before, at least sometimes in the physics literature, so I think there's quite a bit of variance here in how renormalization group transformations, Wilsonian renormalization group transformations are interpreted. There's not much philosophical literature on this, but Harlander and Rosala got this paper actually about the naturalness problem, but in the context of trying to deflate the naturalness problem, they argue that we should really understand Wilsonian renormalization group transformations as relating equivalent models after all. The idea, one limitation of this idea is that that's only going to apply to coarse graining transformations which keep, say, the partition function exactly invariant, so what's sometimes called exact Wilsonian renormalization transformations. And many of the kind of practical applications of the renormalization group don't employ exact renormalization group transformations. They introduce various approximations in the context of implementing a coarse-grained transformation, in which case you're not going to exactly preserve the partition function, so it doesn't look like you can really say that that the models related by those kind of transformations are physically equivalent. However, you could view this as kind of the approximative coarse-grained transformations as parasitic upon these kind of exact versions, and then say the exact version of the Wilsonian renormalization group, that can also be understood as a kind of invariance property. So then you wouldn't have this problem necessarily of radically different interpretations of the Wilsonian renormalization group transformations and the kind of Schugelberg-Peterman renormalization scheme transformations. So that's another idea. There, you still don't necessarily have a story about why, even if you had a common interpretation, you don't necessarily have a story about why these two structures, they're still formally distinct, so there's still a question of like, do they have some kind of common origin, which would be one kind of the most ambitious way of kind of unifying the different renormalization groups, would be if you could tell some kind of story about why the different, about the origin of the different renormalization group structures and kind of these key properties about non-trivial scaling properties and ambiguities and invariance and the transformations between these ambiguities. So yeah, if you could locate all of these features in some kind of more basic features of quantum field theory, that would be one really nice way of trying to unify all of the different renormalization group concepts. And I don't really, so I have, I put a fanciful story here. This is kind of something that's occurred to me, but I'm really not sure about whether it's correct or really a good way of thinking about this issue. But I thought I would talk about it anyway to see what you guys think. So one thing I was kind of I'm interested in thinking about is the idea that the fact that you have products of singular distributions, which is the origins of the ambiguities in perturbative derivative, you also have products of singular distributions in non-perturbative objects that are used to define what a quantum field theory is non-perturbatively. So things like field equations and the commutation relations. So one idea might be, the fact that in QFT you have these singular objects being multiplied together, that's really the kind of core, that's kind of the origin of these properties, which are called renormalization groups. So the idea would be, the fact that products of singular distributions aren't uniquely defined, they introduce this kind of ambiguity. That's what gives rise to ambiguities in the dynamics in both perturbative contexts and also potentially non-perturbatively. So you might try and generalize to a non-perturbative context. And then the fact that these ambiguities are parameterized by a massive parameter, so something like a renormalization scale, that's actually what makes dimensional transmutation possible and running couplings. So the idea there is basically like, if you didn't have a renormalization scale parameterizing the ambiguities, then dimensional analysis would tell you that dimensionless quantities like the coupling, they should be scale invariant. They shouldn't depend on the external momentum scale. Once you have a renormalization scale coming in, which originates from ambiguities, coming from products of distributions, then you can introduce a kind of indirect dependence on the renormalization scale. So that's really what allows quantum field theories to have these kind of much richer scaling properties than other types of theories. And I was just going to mention that I don't understand any of this work, but there are some people who are trying to generalize this notion of a Stuckelberg-Peterman renormalization group, so a transformation between different ambiguities which essentially arise in the products of distributions from perturbation theory into a non-perturbative context. So some of this kind of mathematical physics work that people who work on causal perturbation theory, which is kind of the successor of this approach that of Stuckelberg and Peterman that I was talking about right at the beginning. I'll just read some of this out. So they say, in contrast to classical theory, in perturbative quantum field theory, the field equations alone does not in general completely fix the dynamical evolution. There remains some freedom which has to be fixed by additional conditions, renormalization conditions. These can be classified in terms of the Stuckelberg-Peterman renormalization group. And then later on in the paper, they're kind of trying to argue that similar to the perturbative case, also in the non-perturbative framework that they're trying to develop, the dynamics is not completely fixed. Essentially, you get some kind of ambiguity in the dynamics and then some kind of transformation between different ways of fixing that ambiguity. Which would be one way of, like, if you can tell that kind of story, then you wouldn't have this problem of relating perturbative and non-perturbative versions of the renormalization group. Just to conclude, some worries about what I just said, though, or this kind of fanciful story. There's a confusion in my head to some extent about how this could be consistent with the effective field theory picture and the kind of Wilsonian approach in general, where you work with a theory with an ultraviolet cutoff. So how could the kind of singular behavior in the ultraviolet be explanatory, essentially, for explaining features of quantum field theories? Because, yeah, these distributional ambiguities basically come from multiplying objects at coincident spacetime points. So that's not going to be an issue in a cutoff theory. The other issue is that, that story sounds very tied to kind of peculiar features of quantum field theory, the fact that you have these singular objects in quantum field theory. But we know, renormalization group methods work really well in other areas of physics and even beyond physics. So yeah, it doesn't seem like this story is going to give a very easy answer to that question of why renormalization group methods work so well across the board rather than just in QFT. And that's kind of all I've got basically. So yeah, thanks very much for listening.
Thank you. So I'll open up the queue for questions. I'm particularly interested in if any students or postdocs have questions to start us off today. David, you're not a student or a postdoc.
In the queue after the students and postdocs.
It's kind of bright in here. If I'm missing anybody, jump in. If I don't see anybody, so, I'm sorry, Adam. Yeah, okay.
So I wanted to ask a bit about how you see the relationship between Wilsonian.
Could you speak up just a little bit?
You can use the mics.
Does that help?
Yeah.
I have it
Oh,
on.
yeah.
Cool. So I wanted to ask a little bit about how you see the relationship between the Wilsonian renormalization group and the sort of Gelman-Lowe. So at least the way I understand it, and this, I might be anticipating at least one of David's questions. We chatted about this a bit, but that sort of the background structure of how you get at a renormalization group is quite different. But in the end, the sort of flow induced, these beta functions you get, the theory space you set up, are going to be roughly the same.
Mm-hmm.
And so what do you take the Wilsonian renormalization group to be? Do you think it's the transformation of integrating out degrees of freedom, or the resulting beta functions that come from that?
So are you kind of asking a question how we should individuate? You could individuate renormalization group structures by the flow basically, or by the beta function, because that essentially gives you
Yeah, because I think I agree in some sense that the sort of integrating a degree of freedom gives you a much more general picture. But then when you transitioned into this flow on a theory space, once you've got a theory space set up, you have a reversible transformation in terms of the complexity of a flow that goes one way or the other. You're not, you're relating equivalent theories in the sense that they give the same endpoint functions. And so in some sense, once you at least get to that point, they do seem a lot more equivalent than it might seem otherwise.
Yeah, I think that the this one's scrolling very well. Yeah, so you're talking about this relationship between the definitive Wilsonian IG and the Gell-Mann-Low renormalization group. So it could just be that my formal understanding is insufficient here, but I at least still hadn't understood that being a relationship of reference.
Yes.
Yeah.
Yeah, I think that there's room in there, because I think, again, you can use sort of Wilsonian transformation to generate inequivalent theories, but once you integrate out a field and arrive at a different theory that does not contain that kind of field or whatever. But I think, yeah, so I don't know exactly, I need to think about this a bit more too. I don't know exactly how to think about it, but at least once you get to the theory space, flows in the theory space, it seems like they could be the same type of answer.
Yeah, they're very closely related at least, yeah. It's a very close relationship. Yeah, I kind of like that way of thinking in terms of using the theory space and the flow as kind of two transformations which generate the same flow, or in some sense the same renormalization group. I share that intuition. So I don't think that is exactly the case between the Gell-Mann-Low and the observative Wilsonian RG. But yes, that's definitely one of the most important relationships for kind of telling some story about unifying these approaches. I guess one thing to mention though here is that, as I said, the Gell-Mann-Low transformations are kind of really a small subset of the transformations between different renormalization schemes. So yeah, one question that I had in my head was like, is there a non-perturbative generalization of that? Like, are there other transformations that, in addition to transformations between different renormalization scales in like the Wilsonian, not in the Wilsonian context, but in a non-perturbative context? Because otherwise you are still going to have this kind of slightly strange disanalogy between the full set of transformations between different renormalization scales, and then the information that you get from the Wilsonian approach. So yeah, that's kind of, even if what you were saying was correct, and you can really tell a very close story about the relationship between these two things. I don't know if that completely resolves it. Yeah.
Okay, so on my list, I have Emily, and Chris, and David, and Noel, and Bill, and Alex. Okay, and I see more hands. So I'm gonna go with Emily next.
Great, thank you. Yeah, I just wondered if you could maybe say something more about the reversibility or otherwise incorporating transformation. Because people seem to say somewhat contradictory things about this sometimes, but sort of the general picture, as far as I can make it out, seems to be that no implementation is going to give you a true group. They're all irreversible at fixed points, and so they're all semi-groups. But people mostly seem to expect the transformation to be reversible away from the fixed points. That people do sometimes reverse transformations and go down to prove asymptotic freedom or whatever. And I guess I would have thought that if you have two transformations and one of them is reversible and one of them is not reversible, then it can't just be a sort of convention as to which one is right, because if the reversible one is right, we should be able to infer high energy Lagrangians from low energy Lagrangians, and if the irreversible one is right, we shouldn't be able to do that.
Okay, I was understanding the start of your question, but then I didn't quite. You said I wasn't sure who you were attributing the view you were disagreeing with.
I'm just wondering if you could say more about specifically, should we expect the cross-braiding transformation to, in general, be reversible away from fixed points? Or?
Yeah, so there is a bit of a issue here about exactly what you view as part of the coarse-grained transformation. Because as I was saying, so there are what are called exact Wilsonian renormalization group transformations, which keep the partition function kind of completely invariant. And in general, I expect that will be reversible. But if you look at the way that people employ renormalization group techniques in practice, they often, typically they aren't employing a kind of exact coarse-grained transformation because there will typically be some kind of approximation involved in the implementation of a coarse-grained transformation, which kind of inevitably leads you to throw away information. So for instance, if you, in order to make the transformation exact, you would have to keep track of an infinite number of non-renormalizable terms.
Yes.
And you don't do that, basically. So almost always people are like throwing away at least some of the information that's encoded in the non-renormalizable terms. So the exact, there's kind of like an exact thing, which is quite a like formal, formal in the sense of can be discussed abstractly, but isn't actually used that much in most practical applications. And then a lot of the time, but you could view that as fundamental and then some kind of approximation being introduced, and that's what's leading to like a non-invertible transformation. So I think that was kind of, I don't think I really explained that very well, but that was part of what I was thinking about when I was talking about the Rosala and Hollander view that you could view the Wilsonian renormalization group as relating equivalent theories, but it seems that's only going to apply to the exact versions, and then there's going to be loads of stuff that people are doing and using the term renormalization group transformations that aren't going to fall under that heading.
That's very helpful.
Yeah.
David has here.
Just briefly, one way to think about the difficulty of flowing to high energy, if you're doing the infinite coefficients, you can formally go in both directions, but all but a finite number of those coefficients are irrelevant, so they blow up at large energies. If you're lucky, none of the coefficients are relevant and blow up at low energies, and if you're unlucky, only one or two of them do. So generally speaking, on any given truncation, flowing to high energy your approximation is going to break down relatively quickly, with flowing to low energy is safer. But that's not to do with formal reversibility, but it's to do with the reversibility of truncations.
Okay, Chris?
Yeah, so this is more of a methodological question, and I was thinking in terms of an analogy. So people often talk about whether Newton used the calculus in the Principia, for example. And this is a similar kind of question about exactly how to think about mathematical methods in physics. And I often think of that as just a misplaced question. The question is rather what types of problems was he able to solve and what techniques did he use to solve them? And so rather than thinking of there being a question of, at some level of mathematical doctrine, how did what Newton had compared to what Leibniz had? It's sometimes more interesting to ask what were the problems that they were able to solve and what techniques did they use to solve them and how did those compare? And I think that might be useful. So like Niccolo Guicciardini in particular has sort of pursued this line on Newton. But as you're talking, I was thinking there's a question of what were the sets of problems that people were using the renormalization group to solve? And then that puts into relief the question of what's the impact of having a unifying strategy, right? So if you have a unifying account, then it would allow you to transfer problem-solving techniques from one domain to another. And so I'm wondering if that's one of the reasons why people were sort of pursuing unifying strategies, and then also new insights. So there are a lot of things that you didn't mention that I'd be interested to hear about, like the importance of Gaussian fixed points, that kind of thing. Like, did that come about as, moving from sort of just the Gelman-Lowe formula to thinking about the analogies that arise when you have the Wilsonian view, like those other aspects that we think of as associated with renormalization group techniques? How did those come in, and were they reliant on the assumption that there's a unifying story here, or how to think about that? So it's partly what's the impact of having or not having a unifying strategy?
Yeah, that's really interesting question, and it's something that I have thought about to some extent. I mean, one thing because I've sort of been doing some historical work, which naturally leads, that's kind of the natural way to pursue that kind of project of, what were the problems leading these techniques to be developed. Because it's definitely the case that the problems change, and I think that's. So I've got one historical paper, but I've only really done the history of the 50s, so like the early organization group, and I kind of use that sort of narrative to explain why these techniques don't catch on basically in the 50s, because the Zuckerberg-Peterman version didn't really have any practice. It was addressing a problem, but it was more, the problem was a conceptual problem to do with the interpretation of renormalization, adaptive renormalization, basically. And then the Gelman-Lowe version was addressing this question of the ultraviolet behavior of QED, which kind of basically the conclusion that they draw is like perturbation theory doesn't tell us about this. So it's not it's a negative conclusion, and therefore it's not clear like where you go from there, which is the main reason that people were going on about the renormalization group concept in the 50s and 60s particularly. And then yes, like that's definitely the way that I want to think about Wilson. I've still not done the history of Wilson properly, but yeah, some other people are doing that as well. So I think that, for instance, that's a really good way of thinking about why the Wilsonian approach is not tied to perturbation theory, because my current understanding of Wilson really is like his big project is to try and get away from perturbation theory, because his drive is to formulate a theory of the strong interaction. Like that's the like underlying problem, and he doesn't have an inkling of asymptotic freedom. So he's thinking, perturbation theory is not telling us about this regime, but we still need to like basically a lot of the concepts, the renormalization concepts in the 50s were kind of intrinsically tied to perturbation theory. So there was a problem of trying to liberate them from that context, and that's the way that I want to understand what what's like driving Wilson basically. Yes, but another thing I was going to say is there is a question here of like, because you were asking what's the practical implications of unification. You could have the view that disunity is potentially a good thing. Like some people have kind of discussed this idea that like it's good for scientific concepts to be malleable and have like multiple quite different ways of cashing them out. So yeah, I think that's kind of an intriguing question as well. Is like, because basically people aren't really pursuing these unification strategies. I mean, I'm kind of like trying to draw on some, like threads that exist in literature, but it's not kind of something that people physicists are really worried about. So maybe that's telling us something that, these kind of some degree of conceptual disunity may be tolerable and even beneficial in some way. Is something that I'm kind of interested in thinking about. Yeah.
No.
So I really like the facts of the story. Really I was wondering if the dilemma you had at the end.
Could you speak that up?
Sorry, so I was wondering if the dilemma you had.
The mic.
No. I was wondering if the dilemma you had at the end was maybe perhaps less of a dilemma than it seems to be, right? Because it seems like for one level, if you're looking at why do like Wilsonian denormalization techniques widely apply across all sorts of areas of sciences, it strikes me like the prima facie, you probably wouldn't expect there to be a super unified explanation there. Something like, well, theories that have certain kinds of nice features allow for this sorts of scaling transformations. And if we find those all over the place, that's cool. Maybe there's a kind of general explanation, but that would be kind of astonishing. So then the thought is something like, okay, so we can use these techniques all over the place. There's still a question of within quantum field theory, why are they so widely applicable? And it would be really neat if it turns out that the sorts of exact quantum field theories that we have that use distributions, many of them have this sort of nice scaling feature because of the dynamical ambiguities down at bottom.
Yeah.
That doesn't necessarily solve the problem for effective field theories, because there it seems like we just posit them, hope they have these properties, and if they're sort of empirically confirmed, that gives us reason to think that they do, whether or not the underlying theory is something like a distributional quantum field theory. But at least it seems like you potentially have the start of a kind of unified explanation for why we'd expect a large class of exact quantum field theories to exhibit this kind of behavior in the...
Yeah, I mean, okay, so there are two parts of the question. I guess we'll go back to my two worries. I think I'll answer the second one first, about, I guess, addressing more of the first point. One thing I have considered thinking about is, as a way of like responding to this worry, is if you can kind of, if you can associate a phenomenon like dimensional transmutation with the existence of running coupling. So the fact that you have violations of scale, you have like anomalous breaking of scale invariance in QFT generically, basically. I mean, there are conformal field theories, but you have to like do other work. So that's generically speaking, scale invariance is broken by renormalization. Locating the origin of that in the singular behavior of objects in QFT at coincident points, products at coincident points, wouldn't necessarily, I mean, that doesn't require you to like believe that that structure is associated with the real world. That could just be like, in a similar way to, if you take the thermodynamic limits of a finite system and you find multiple equilibrium states, that gives you information about the properties of the finite system. You could tell a similar story about the continuum limit in QFT, that by looking at the peculiarities of the continuum limit, illuminate the scaling structure of theories, even when there is no valid cutoff. So yeah, that might be one way of, which is I think slightly different from what you were saying, and maybe stronger than what you were suggesting. But that's something that I would like to explore if the fanciful story has any merit to it. But then on the question of, yes, on applications outside of QFT, I don't know, I'm kind of less clear there. I mean, obviously, there's this much more general, the Wilsonian renormalization group, the idea of like eliminating degrees of freedom and coarse graining. You can kind of see why that's going to be good. Like, even in the case of theories which, well, the thing is, they kind of do have to have some interesting scaling behavior. Otherwise, it's not going to be very interesting to do that. But there could be different origins. Well, there definitely are different origins of non-trivial scaling behavior. So this would be kind of like one very interesting and kind of weird one that crops up in QFT. Like anomalous scale breaking. But other areas, there are many other sources of like characteristic scales. That's another project that I want to do actually, is to try and like give some characterization of the different ways that kind of interesting scaling behavior can appear in physical systems. So yeah. agreed. I think there are kind of answers here, but.
So we need coffee, and I have David next, but this may be the last question. Maybe we'll get to Alex if
Sorry,
David's fast.
So I'm going to do. All right, let me ask you a very fast one then. Why do you call the Gelman-Lowe and Wilson versions alternative? I mean, the way I think about them is, the Gelman-Lowe process. I want to move the point at which I define the end. I specify the endpoint function values of the lower version. And in the Wilson version, I want to move the scale of the alpha capital. And those both seem perfectly coherent, non-determinate defined notions. Now, it's perfectly true. I want to calculate quantitatively how, say, the charge of the electron changes as I move to the normalization point. Then I'm going to do that in a determinate expansion.
Yeah.
But conceptually, there's nothing determinate about it. Any more
Okay,
than
could you
determinate
explain, you said you want to define your endpoint functions, so with respect to
Well, drop the definition. I know the mass and the 4-point function and the field renormalization at energy mu, and I want to know what they are at energy mu plus delta mu.
and the energy here is like a physical momentum scale.
Yeah. Yeah.
Okay. So that's not what the renormalization scale is, though.
Sure, it is in modern use of the Gamma-Lowe factor. thought it is.
No, it's not. The renormalization scale can be fixed like completely arbitrarily. It's not.
Yeah, I know it can, but it's still a physical quantity that's directly related to something measurable. And I want to, if I want to know empirically what those values are, that's a very straightforward way to do that. I appreciate we're off mass shell.
Yeah.
So sure, it's not a direct scattering of that kind, but it's still a perfectly physically defined thing that I can understand in a non-determinative way inside the theory. These are endpoint functions in the theory. They're defined non-determinatively. They have values as functions of the momentum, and I want to know what those values are and how they change. I could define that in lambda.
Yes. Well, so yes, the endpoint functions definitely have a dependence on the external momentum scale, but that's not what the Galileo parameter is. The renormalization scale is not that.
Okay, so we're not going to resolve this in a short
Yeah, we should talk about it. But they're.
Let me rephrase. That's not what the technical Gelman-Lowe transformations is, as described in the 21st century QFT textbook. What Gelman and Lowe did in the 50s, I don't know.
Well, we can talk about this more. This partially connects to what I was saying about some interpretive kind of disagreement about how to understand the notion of renormalization scheme. Anyway, we should have a conversation.
Sure.
Alex?
No, it's fine.
Okay. So let's thank James again. And anybody who didn't get a chance to ask questions,